This came from a student who contacted me and said he had encrypted a virtual machine, and he noticed that the cryptography looked crackable. And he got me to look at it, and that reminded me of something that I needed to put in this course, which I have not, the points transfer from CryptoHack, I don't think it's 1-to-1, I think it's like 3-to-1 or something, but they do transfer from CryptoHack. Yeah. I made some plan for it, which I've forgotten, but my grader knows. But yeah, CryptoHack points definitely add to your total. And there's a lot of things that are pretty easy in CryptoHack, and then it goes all the way to the top. So definitely go to CryptoHack if you need some points. So this is the one, PBKDF2 and AES, and I realized it's missing from this class. This is actually a very common situation. You want to encrypt something from a password, and there's a standard way to do it, which I was horrified to realize was not in my course, so I wrote this up. So here's how you do it if you want to encrypt something with a password. You use this thing called PBKDF2, which is password-based key derivation function. And it's the same thing you use to create password hashes. It's really quite simple, but this turns out to be a beautiful thing, and I think you'll like it. So here's what PBKDF2 does. It takes a pseudo-random function, a password, a salt, and the number of iterations you want, and the size of the key you're trying to create. And the pseudo-random function is typically a hash function. So you can import this thing, hash library, and if you do help of hash library inside Python, it will show you their PBKDF2 HMAC function. And it's just modeled right after the standard definition. So here's one to do. So let me do one of these live. So I don't think I need to import anything. Got CryptoDome installed in Python 3 Interactive, which I've got here. I'll import hashlib. And now I can calculate one. So here is a key generated from a password. All right, so all this does is here's my password, Apple, and you can add a salt, but my salt is empty. I didn't use a salt, and I did one round of MD5. And then I got 16 bytes out of it. So there is a 16-byte key generated from the word Apple. And it's not random, by the way. There's no randomness here. It's just hashing. So if you do it again, you get exactly the same value. And that is the point. You get the user to give you a password, and that password gives you the cryptographic key. Now you store encrypted data, and you don't store the password anywhere. You have a bunch of encrypted data. You'll see this warning on things like password managers. We've got encrypted data. We can't get in there. Nobody on earth can get in there. And if you forget your password, you're toast. Because your password is the key, and we don't have the key anywhere. We haven't stored the key anywhere, and we haven't stored your password anywhere. This is how you do it. So, all right, you can get a 4-byte calculated one there to go. And now there's an issue here of type conversions to convert from strings to integers to byte arrays that you have to do to use some of these things. That's why this is not a string, it is a byte array with the B in front of it, and so is this. You can't use strings, you have to use byte arrays. And so I made a little page of conversions to show you the way to convert integer to and from string, and integer to and from bytes, and string to and from bytes, because I have to do this all the time in Python. And, all right. So now you got a challenge to crack a pin. And, all right, so here's a 3-digit number, and the hash value is this, so you have to calculate them all and find this. So that's cool. Now, the next thing, that's how you make the key. But here's what you really do when you encrypt data, and you use PBK, DF2, and AES together. And this, by the way, is what everybody does all over the place. And the reason I got into this is because Android apps do it all wrong. They're appalling. And I spent several years researching thousands of Android apps, and almost all of them use cryptography wrong. And I decided to teach this course after seeing that. The developers and their managers clearly have no idea what's going on in cryptography, and they just do stuff wrong. You could do it this way, and then the password is not stored anywhere on the phone, which is what you want to do. But they just store a copy of the password on the phone and then try to hide it, which is outrageous. Anyway, so You import hashlib, and you import AES. Now you have some clear text to encrypt. So I just chose a famous quote from somebody, I think Abraham Lincoln. And I made sure, since I'm going to be encrypting this with AES, I made sure it's a multiple of 16 bytes long. That's why I put a space at the end, because AES needs those blocks to be full, or I'd have to pad it somehow, and I didn't want to bother with padding. So you take the key. I'm going to use that same thing from a password of Apple. I'm going to generate a key. 16 bytes is 16 times 8, 128 bits, so it's fine for AES 128. So now I define a cipher based on that key, and I'm using ECB, so I don't need an initialization vector. And now I just encrypt the clear text and print out the ciphertext. So that is this string encrypted with the password that came from from Apple and turned into a key. And you can decrypt it, of course. Here's the code that does that. So you start with the hex, and you use bytes from hex to turn hex into bytes. It can be salted, but I did not put in a salt. The function allows you to salt it, but I left the salt empty. So that's not a very secure. This is not a very secure choice. 1 round is not very secure. No salt is not very secure. MD5 is not very secure. This is not the strongest choice. But you can do it this way. And anyway, so now I can just decrypt it with the key that came from Apple and get back my plain text. And as you see, it works just fine. All right, but this is a very simple version of it and not the most secure. And now a couple of challenges here you can do. And here's the article I found that got me. A student told me to look into this, and I found this article, which is pretty awesome. Although I forgot to make it open in a new tab, but anyway. This article is from Elcomsoft. There are 2 purveyors of hacking software to hack into phones, Elcomsoft and Cellebrite. Cellebrite in Israel and Elcomsoft in Russia. Both of these are companies that will hack into anything for a price. And they claim to have the ability to hack into every version of the iPhone at Cellebrite. I think Elcomsoft can do it too, and they can just hack into almost any encrypted anything. And they often publish interesting articles about how they do it. So here's encrypted virtual machines, Vmware, Parallels, and Virtualbox, showing how they do it. They all use this system we just described, but they make surprising differences. So you encrypt your virtual machine, and it'll tell you put in a password. And then it will scramble the files in the virtual machine based on that password. Parallels uses 128-bit AEC. It uses 2 iterations of MD5. Almost what I just did is what Parallels did. And they say, since that is so weak, you can try to crack it from a list of passwords, and you can do 19 million passwords per second, because you just have to do 2 rounds of MD5. So that is really weak. That is like Microsoft Windows password hashes, which you're cracking if you do the Python projects I just added, which are also incredibly weak. Microsoft Windows password hashes use 1 round of MD4 because they were designed in 1993. They are so old that MD5 had not been written yet, and Microsoft never updated it. So these are incredibly weak salting algorithms, hashing algorithms that really are easy to crack. You can try 100 million or 1 billion passwords in a reasonable amount of time. Now, Vmware uses AES 128, but they use 10,000 rounds of SHA-1. So that takes a lot longer to do each trial, and that means you can only do 10,000 passwords a second. So that still means you can try a lot of passwords, but you can't try so many. And Virtualbox is bloody awesome. They use AES with 128-bit or 256 key. They use SHA-256, and they use 1.2 million iterations. So you can only try 15 passwords per second to crack this. So you could use like the name of your dog, and it would be fine. You know, here you can't have your password be any of the top 10,000, or maybe the top 100 times 10,000, or you'd be caught. And here you could hardly use any password at all. You have enough time here to try almost every password you can think of. But here if your password is like not in the top 1,000 passwords or something, you're probably fine. Probably just the name of your dog, your license plate, or your phone number would be fine. Nobody's getting in there. Anyway, so I have VMware, so I made an encrypted VMware virtual machine, and we'll crack it. So, I made an encrypted. If you encrypt a VMware virtual machine, the VMX file, which normally has configuration lines describing the type of hard drive and stuff, is encrypted, and it starts with this line, encryption key safe, which is all you need. This is the way everything is done with stages. This is the key safe. And you see it's in a little bit hard to read, but it's got a key list pair, and it's easier if you substitute these characters with their translation from URL encoding. So I substitute the punctuation marks, and then add some line breaks, and that line looks like this. Encryption key safe, this tells you how it works. VMware key, list, pair, phrase, and all that jazz. Then there is some data here, which it turns out is unimportant. That's just like an ID number for the virtual machine, which we don't care about. It's not related to the encryption. Then you have the algorithm, which is PBKDF2 HMAC SHA-1. So they're using SHA-1 hashes. They're using AES 256 and 10,000 rounds. And this is the salt in base 64 notation. And this is the encrypted data. First comes the IV, and then the encrypted data. That's it. And this whole thing is called a key safe. This is some data stored in a safe that can't be opened. This is the software equivalent of the secure element on the iPhone, or the trusted platform module on a Microsoft Windows machine, or the simulated secure element on an Android phone. This is how it works. So I'm trying to hide a secret here, and I hide it this way, and the password is not stored anywhere. You have to give it the correct password, and then it will be able to use this algorithm to find the key to open this. So this is how you store secrets. And that's it. So this is the code that will crack it. The only thing you need is these things that are bolded. So you need to, you have to convert this base 64 into bytes. That is the stuff starting with L. This stuff here is the data section. So you convert it from that, from base 64, and then you convert it from hex to bytes. That's the data. The IV is the first 16 bytes of the data. The ciphertext is, I'm just going to choose the next 3 blocks of data. So I'm not going to decrypt all the data. I'm going to decrypt the start of the data because that's enough to see what we need. It's different than Argon 2 because you can get the password back from the hash. No, you cannot get the password back from the hashed password. That's the point. You cannot get it back. You have to perform password cracking, and password cracking just means starting from a list of passwords and hashing them until you find a match. That's why the strength of a password hashing routine is measured by how many millions per second you can try. And this one will let you try like 10,000 per second. But there is no, in principle, way to reverse it. You have to guess it. So if you guess a password that is not in any password list, then nobody can crack it. Because nobody has enough time to try every combination of letters, unless your password is really short, like 6 or 8 letters. If your password is at least 10 or 12 letters long, then the only way anybody can ever get it is if it's in a list somewhere, or if it's a small variation of something in a list. So the salt is B64 to hex to bytes. Yes, exactly. And so is the data. You commonly store these things in base 64 because it's a little more efficient than storing the hex values. Sure, here's the LcomSoft link, which is really good fun. Yeah, base64 is more compact because it has 6 bytes per character instead of the 4 bytes per character, which is what hex has. So really, they store the same information. Base64 is just a little bit more compact. That's all. So here's the data, and there's the IV. Here's the ciphertext, which I'm going to just decrypt the first 3 blocks of the data. So I get the salt. The salt is from here. So once again, I have to take the salt value and reverse it from base 64 and then make bytes from hex. And now I calculate the key. The key is just from this PBKDF2 thing, HMAC, SHA-1. Now I need the password, and I made this machine, so I happen to know the right password is 123123. It will let you use 6-character passwords. Then the salt, which I got from here, 10,000 rounds, and I need 32 bytes of data because they're going to use AES 256 from this. That gives me the key. Now I can just decrypt the ciphertext. So this code right here will decrypt the stuff stored in the key safe. So let's do that. All right, and now you can see what was in the key safe. It is readable stuff. Type equals key. What's stored in the key safe is another key, and it is an AES 256 key, and here it is, and this is the start of it. I didn't decrypt it all. This is the beginning of it in base 64. So the way this works is they made the key safe to store something from your and they can only open the key safe if you put in the password, and what's in the key safe is another AES key, which is what's used to encrypt the other data. This is very much like RSA. Remember, RSA is a way to securely send data over the internet, but what you do is you just send an AES key, and then you use that from then on. This is generally the most efficient way to do anything because AES is secure and fast. The only problem with AES is you have to deliver the key somehow. So your password unlocks the safe, and the safe has the key, and then you use the key to encrypt the hard drive and decrypt it. So they did store the key to the hard drive, but they stored it in a safe that can only be opened by your password. So this is pretty brilliant, and it's not that hard to crack. So that's how it works, and now you got some challenges. So I made a safe with a real simple password that is 6 digits, but I doubled the digits, so it's 112233. So there's only 1,000 possible keys. So you'll be able to crack this one pretty fast. And then there's the one my student originally sent me. A student sent me an encrypted virtual machine and said, can you break in? And it was an 8-character key, and I said, no one can get in, it's going to take forever, so he gave me the first 2 characters and the last 2 characters. So it's got an 8-character password, which starts with WE and ends with SS, and the 4 characters in the middle are lowercase letters. So it is 26 to the 4th possibilities, which is not impossible. So crack that safe. Here's the data from his virtual machine. And I was able to get in, and it didn't take too long. In the worst case, it would have taken 1 hour of calculation, and in fact, it took a lot less than that. So there's a ton of points to be made here, like 90 points, of all extra credit, of course. But check it out. This was a big hit at Black Hat. It's very fun because just this is the way to use a password and to hide something. See, this is what should be happening on your phone. This is what's happening on your iPhone. Your iPhone needs your PIN, and it really can't get in without your PIN. And this is what Android apps should be doing, and they totally are not doing it. It's appalling. They're storing your password on your phone in the data storage of about half the apps on your Android phone for no good reason, instead of doing this stuff. Because the people that write those apps just don't understand cryptography and they don't use it correctly. Anyway, that's what I wanted to show you, and check that out if you like. And of course, as a student said, if you don't want to do this math-oriented stuff, you can go do other things like CryptoHack, and that's fine.